Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into the fascinating world of AMD's Zen 5 architecture, specifically its unique front-end setup and the surprising implications of disabling its op cache. Get ready for some serious tech talk.
I'm pumped. So Zen 5 has this dual fetch and decode cluster setup, right? What's the big deal?
Exactly. Each cluster serves one of the core's two SMT threads, reminiscent of the older steamroller architecture. Both can decode up to 8 instructions per cycle with 2 threads, or 4 with 1. But that's where the similarity ends. The key difference is Zen 5's massive 6K entry op cache.
A 6K op cache? That's huge. So the decoders are mostly idle then?
Pretty much. The op cache handles most of the instruction stream. This makes evaluating the decoders tricky, but luckily, there's a way to force them into action. You can disable the op cache by setting a specific bit in a particular MSR register.
Clever. So you did that, right? What did you find?
Yep. With the op cache off, a single thread is limited to 4 IPC, as expected from a 4-wide decoder. But with 2 threads, we hit 8 IPC, utilizing both decode clusters. It's a 2x improvement.
That's impressive. But, isn't this completely unrealistic? I mean, who's going to run Zen 5 with the op cache disabled?
You're absolutely right. It's not a real-world scenario. It's more of a controlled experiment to understand the decoder's capabilities in isolation. Think of it as a stress test, and the results are interesting, especially when compared to older architectures like Excavator.
How so?
Excavator, while also having a clustered decoder, lacks Zen 5's dual fetch paths. This means Zen 5 handles L1 and misses far better, especially with 2 threads active. It's a significant architectural improvement.
Interesting. So what about real-world benchmarks? How did disabling the op cache affect performance in something like Spec CPU 2017?
Big hit in single-threaded mode. A 20.3% drop in integer and 16.8% in floating point. But with SMT, the impact is much smaller, 4.9% and 0.82% respectively. The dual decode clusters really shine in multi-threaded scenarios.
Wow, that's a huge difference between single and multi-threaded performance. So the op cache is crucial for single-threaded performance, but the dual decoders help mitigate the performance loss in multi-threaded workloads?
Precisely. High IPC workloads suffer the most from disabling the op cache, while lower IPC workloads are less affected. Games, for example, showed minimal performance changes with the op cache disabled. They're generally low IPC workloads and don't fully utilize the op cache's high throughput.
So what's the overall takeaway? Is the dual decoder setup a good design choice?
It's a smart design. While a single 4-wide decoder isn't ideal for high IPC workloads, the dual cluster setup excels in multi-threaded scenarios. It's a secondary instruction delivery mechanism, stepping in when the op cache can't keep up. It's all about balancing single-threaded and multi-threaded performance. And Zen 5 does a remarkable job.
It sounds like a really clever engineering solution. Thanks for breaking it down.
My pleasure. And remember, folks, if you enjoyed this deep dive into the intricacies of Zen 5, consider supporting Chips and Cheese on Patreon or PayPal. You can also join our Discord community for more tech discussions. Until next time, goodbye.
Bye-bye.